Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. Pardon me for the quite late video upload because I was studying up with the schedule. Let's move on to the chapter 2, which is thermodynamic property relations. And as the name applies, so the course objective, the topic sub-objective will be, the first one is to develop fundamental relation between commonly encountered thermodynamic properties and express the properties that cannot be measured directly in terms of easily measurable properties. This is really important, right? Because especially if you have this kind of question that does not, or maybe requires you to use the relation between another properties that you can measure with something that you cannot measure directly. So this is really important, the knowledge of this, so that it will be much comfortable for you to derive the answer towards the answer. And the second one is to develop the Maxwell relation. The Maxwell relation is really important in chemical and thermodynamics, which form the basis for many thermodynamic relations. And next one is to develop the Clapeyron equation and determine the enthalpy of vaporization from P, V, and T measurements alone. And next one is to develop general relations for CV, CP, DU, DH, and DS that are valid for all pure substances. Okay, we'll start with partial derivative and associated relations. Okay, the state postulate is, it is a state of a simple compressible substance which is completely specified by any two independent intensive properties. Okay, and all other properties at that state can be expressed in terms of those two properties, which are z equals to z to the function of x and y. Okay, so this is the example. So we can see here that this is the function of x and y. Okay, the derivative of a function fx with respect to x represent the rate of change of x with x. So this is what it means, or this is what it implies, because f equals to function f, the derivative of the function f with respect to x, which represent the rate of change of f with x. F is just an example. For example, it can be u, it can be h, it can be s entropy here. So this is the limiting relation, the limiting factor, and this is what you get, especially derivative of a function fx plus delta x minus f derivative of a function x per delta x. So this is by definition, you can see the function of this x plus delta x minus fx. So this one, you get this one, and minus this one, which is the delta of x, the changes of x, because this is the same, right? X plus delta x. So basically, this is how it means the partial derivative, because this is really important, because in this chapter you will count a lot of partial derivative. And next one is partial derivative of z is the variation of z to the function of x and y with x when y is held constant with respect to x, and it is expressed as this, which is partial derivative of z per partial derivative of x with y. So in this case, we can see that as the geometric representation of the partial of this partial derivative, so this one applies, where the y is held constant, right? Because y, we can see here that y is constant, y is not moving, y is just one spot and one line, and z, it is the variation of z z over x, which is this one, z over x, because it is changes it is changing. So this is what it means, whereby you can get the x plus delta x y minus z to a function of x and y. So the symbol, this symbol denotes differential changes. What is different? Okay, the symbol for D is the total differential change of a function and reflects the influence of all variables, and this symbol reflects the partial differential change due to the variation of a single variable. Okay, so this is the difference, which is very significant, and the changes indicated by D and partial derivative are identical for independent variables, but not for dependent variables. Okay, so that is clearly different if you want to compare with the previous definition of D, which is the derivative. Okay, next one is to obtain a relation for the total differential change in z to the function of xy for simultaneous changes in x and y. Consider a small portion of the surface, which is according to this figure. This figure is the geometric representation of total derivative dz for a function z x y when the independent variables x and y change by delta x and delta y respectively. The dependent variable z changes by delta z, which can be expressed as this one. Delta z equals to z to the function of x plus delta x y plus delta y, because we can see here the changes of this minus z to the function of z and y. So this one minus this one. So you can get this point, okay, because you want to observe the difference of delta z, right? This delta. So which implies by this one's minus this one. So this is what it means. Adding and subtracting x z y plus delta y, we get this one. It's quite a long term, or we can simplify it into this one, delta z. So basically this is how you want to express something, or the relation for a total different change when it involves x, y, and z, and taking the limits of this using the definition of partial derivative. So we can get a simplified one, which is the dz equals to partial derivative z per partial derivative per x and to the power of y, and the x plus partial derivative of z and y over x times it towards dy. Okay, so this is the simplified version. Basically, this is just to explain to you the understanding of D, which is the total differential change, and this one, this symbol, which is the partial differential change. Okay. Okay, this is the fundamental relation for the total differential of a dependent variable in terms of its partial derivative with respect to the independent variables. Okay, next one is we have partial differential relation. Okay, from this equation you can see m partial differential of my equals to partial differential at nx. We can get from this point that xy minus, and then after several rearrangement, and after we substitute with m equals to z per x and n equals to z per y. So we substitute over here and then we rearrange it, and then we can get this reciprocity relations and this one cyclic relations. This is really important because as I mentioned previously, this chapter is about how you want to derive something that you cannot measure directly. So that's why these are the fundamental and the principle that you really have to understand, so that it will be much comfortable for you to develop the relations afterwards. So this is the example. We can see here z plus 2xy minus 3y squared z equals to 0, and then from the function we can get z equals to 2xy per dy power of 2 minus 1, and then we want to make it into the partial derivative. Then we can get do y per 3y squared minus 1, and thus for number 2 is how about z and equals to 3y. If let's say we want to convert, so we have to rearrange it z and then rearrange everything, we can get this expression, and then we want to make it into partial derivative of x, then you can get this term. So it means that this is what it means by that. We need to say that the partial derivative of z over x equals to the reciprocity relation, right? Because we can see here that this is like reciprocity, like this one applies, right? So that is the fundamental of or the principle of the reciprocity relation. Sorry. Okay. Next one is we have several types of thermodynamic properties. The first one is the measured properties, which are P, V, T, and composition, and the fundamental properties like internal energy, U and S entropy, and the derived thermodynamic properties like H enthalpy, Helmholtz energy, and Gibbs energy. Okay. Okay, when we talk about this, about the entropy, so if let's say the entropy give the value which is more than 0, it can be regarded as spontaneous, and if it is like equals to 0, which is the entropy, the delta of entropy in system plus delta of entropy in the surrounding equals to 0, so it means that it is reversible or it can be equilibrium. Let's say the system is in equilibrium, so you can assume and you can just signify that the delta S is 0. Okay. Okay, next one is entropy and Gibbs free energy. Okay, how are entropy and enthalpy is related? So we can see here from this equation, this is also an important equation, delta G, which is Gibbs free energy in joule or kilojoule, equals to enthalpy minus T delta S entropy. So Gibbs free energy is the energy that is available to do useful work, and a reaction will spontaneously occur if delta G might less than 0, which is exergonic reactions, and a reaction will not spontaneously occur if the delta G is more than 0, which is endergonic reactions. Okay, let's consider the following reversible reactions, AB yields C plus D, and the following equation relates the standard state free energy of a reaction with the free energy at any point in a given reaction, not necessarily at standard state conditions, whereby delta G equals to delta G standard state free energy plus RT ln Q. So ln Q is the natural logarithm of the reaction coefficient. So remember that the constant is 8.314 joule per mole Kelvin. And so this is another formula for uh, measuring the free energy at any moment, which is the Gibbs free energy. Okay, so this is the back to the previous one, so which is delta G equals to delta H plus T delta S, which is this one, and then delta G equals to RT ln KT, which is the dissociation rate. So this is actually interrelated to the same delta G. I mean to say that if you get this delta G, you can find this value if you have all the available value for this delta G. Then make sure that the unit is consistent, yeah, especially consistent to the uh, gas constant. Okay, next one we have the Gibbs free energy and how we want to derive it. And next one, okay, the first one we start with the delta S. Okay, delta S, which is entropy equals to enthalpy per temperature. So which is negative delta H system, and the S universe, delta S universe, like this one implied before. This formula. Okay, then from this one you can get delta S surrounding, and you can combine 1 and 2, which is this delta S, and you can rearrange it, and you can replace this delta S into this one. So you can get delta S universal equals to delta S system minus delta H system per T, and then multiply by negative T, so everything will be negative T, and then this T will disappear, and rearrange the equation so you can get this one. And after that you can define the Gibbs energy, which is Gibbs energy negative Ts. Yeah, this one. Which is Gibbs free energy equals to negative T delta S. And then we can get this delta G system equals to H system negative T, because this one can be defined by delta G system of a system, yeah. So don't get confused. This is for the system and not for the reaction or for the any kind of uh, dissociation rate. Okay, so you can get, after that you can get delta, and when you combine these last two equation, so you will get delta G system equals to this one, equals to this equation, so you can get this equation. This is how you get this equation, which is for the Gibbs free energy for for a reaction, for a system. Okay, so basically this is delta G for the general formula. And then for the delta G reaction, you can get the total of G products minus total Gibbs energy reactants, and then you can get the total Gibbs energy reactions. Okay, for delta G reaction, the formula is like this. Is this one RT? So this is different, yeah. So don't get confused, because this is for delta G reactions, and delta G. Okay. Because okay, another one is make sure you don't get confused because this one is KD, which is the dissociation rate, and this one is long Q, right? So this one is the delta G reaction. So you can insert this one. You can insert this definition into. Sorry, this one. This is not proper. So this one you can insert this one into the delta G, and then you can get the G reaction, and then you can get the combination of it, which is RT on Q per K equate K, what is that, dissociation rate. All right. Okay, please take note that if let's say you get the delta H is negative, it is exothermic, and if it is positive, then it should be the endothermic. Okay, I have one question for you. So make sure you, okay, based on the question, consider the following enthalpy and entropy data for water in both liquid and gaseous state, which is given here. So what is the free energy change for the vaporization of water at room temperature? Okay, so this is the Gibbs free energy, and all the formula is given. So let's give it a shot, because I believe that every data is given here. So, and also from the derivation, you can get the relations, and how do you want to come out with the free energy change for the vaporization of water at room temperature. Okay, make sure you drop down your answer in the comment section below. And next one. Okay, sorry, this is the answer. Okay, next one is we're talking about Gibbs free energy again, and then if let's say this is just the general understanding. If it is negative, this one is negative, and this one is negative, and this one is positive, then it should be energetically favorable and entropically favorable and always spontaneous. But if this positive and this one is positive and this one is negative, then it's going to be energetically unfavorable and entropically unfavorable and never spontaneous. But if let's say this one is positive and negative, or negative, and this one can be positive and positive, it should be energetically unfavorable and entropically favorable and spontaneous at high temperature. And if let's say it's going to be positive or negative, and this one negative and negative, it should be energetically favorable and entropically unfavorable, vice versa, and spontaneous at low temperature. So this is just the guidance for you. If let's say you can get the value and the based on the statement given here. Okay, another one is let's say if you get the k value to be more than 1, so uh, it should be spontaneous, the system. And if let's say it is which it favors to more to the product, and if let's say the Gibbs energy is in the range of 0 and 1, then it should be more to the reactant, and it should be non-spontaneous. And if let's say the k is almost equals to 1, then it should be equilibrium, because the Gibbs will be equals to 0. Okay. Okay, next one is calculate the value of K at 298 Kelvin for the following reaction given that delta G is negative 32.6 not 96 kilojoule per mole, and then we can get this uh, equation. So this one. So you can get nitrogen plus 3H2 equals like reversible 2NH3. So look at the state of the substance, which is in gas form. So looking back to the equation, we can get the, because delta G is given, so over here we can have the ln K equals to negative delta G per RT, and ln K equals to negative 3296. We have to convert because it has to be according to the gas constant and 298 Kelvin. We can get 13.3. Then after we convert to Lambda, then we can get 5.97 to the times to the power of 5. And the large value of K means the equilibrium lies to the right, which favors to the product. So that is meant by this previously. Okay. So yeah, it can be one of the possibility for the answer for the question. Okay. Okay. Next one is the equilibrium partial pressure constant is 1.4 2 times of negative 5 at 298 for a certain reaction. Calculate the standard free energy change at 298 for that reaction. So again, this is the Gibbs energy, and I believe by now you already know what kind of equation to use. So and this one also, put your answer in the comment section below. Okay, next exercise 3. This is according to, I want to give you one hint, which is this is according to this one, G reaction, yeah. Okay, so calculate the free energy change for the reaction shown below at 298 Kelvin when the partial pressures of SO2, O2, and SO3 are 0.2 atmosphere, 0.1 atmosphere, and 0.01 atmosphere. So the free energy change is given for SO2 and SO3. And what is the free energy change for O2? Please find out for yourself, and then you can get the answer. All right. So again, put your answer in the comment section down below, and I will take a look. All right. Okay. Another one is fundamental property relation. They are the equations that relate the partial derivative of properties P, V, T, and S of a simple compressible substance to each other. They are obtained from the four Gibbs equation expressed as du plus equals to TdS minus PdV, dH equals to TdS plus VdP, and dA equals to negative S dt minus PdV, and dG equals to negative S dt plus VdP. So this is the very fundamental property relation in thermodynamic, and this is next one, which is really important item in this topic, which is Maxwell relation. Maxwell relations are extremely valuable in thermodynamics as they provide a means of determining the change in entropy, which cannot be measured directly by simply measuring the changes in properties PV and T. Okay, so these are the four terms in Maxwell relation: TVPS, TP, VSP, SVPT, and SP and VT. Maxwell relations are extremely valuable in thermodynamic analysis. So this is what I'm telling you, that how you want to relate if it's not, if it is cannot be directly measurable. Okay, looking at this, and I have the first task for you, which is the poster. The total mark should be 10, and I've been thinking that we should make, I think maybe one or at least three. Oh no, sorry, at least two. So this one is one poster, and maybe we can have another one or another two after the semester break. Okay, in your group. Okay, in this case, I will not be dividing yourself into group, which is sorry, it's okay. It's okay. I think after this, I will release the list of your group, and then in your group, please discuss on how you want to derive the Maxwell relation, and you can refer to the internet, YouTube, and do not forget to list down all the resources by proper citation, and please prepare the poster presentation in a creative way, and make sure you upload your assignment, or which is in the form of the poster on social media. It can be on LinkedIn, it can be on Facebook, it can be on Instagram, it can be on YouTube, and whatever. It can be as many as you can, and there's no restrictions for each platform. Okay, sorry. I think to be fair, it should be in only one platform. Okay, only in one platform. So you have to use your wisdom, which platform that you think that you can get more interaction, because you have to give me the proof of how many likes and the comment that you can get. And please make sure that you mention ECH3120 chemical engineering thermodynamics and the lecture's name, and tell me if available. So the task is how do you derive this Maxwell relation? Yeah, from U, from H, from A, and from G. So the hint is given here. Okay, the due date for this will be 1 week. So you have to submit to me next week on Tuesday. All right. Okay. Next task is we have the thermodynamic web. So actually, this is quite straightforward. If you so next task is you can sit down with your group members and try to understand this. Actually, there's so many resources available in the internet that you can refer to. So this is how the cyclic relation is applied, and also the reciprocity, right? So this is how everything and every expression is related to each other. Actually, there's a hint for max relation too in this situation. Okay, so I want you to present this, but this one it should be in the form of video, in the form of video, and in the form of video, and I want you to post also to your social media. And I want to, of course, the same thing also. I want you to make sure that you can get as many likes and interactions, so that this knowledge can also contribute to other people, especially from those non-engineering field. Okay. So these are the hint also. Partial derivative of T, P, S, and V are related to each other and to the reported properties of CV, CP, beta, and K. Okay, so I believe that's all for this session. So that's all for this session, and for this week, I'm giving you two assignment, because for the first week, I don't give you any assignment, and I just like the normal exercise in during the session. So I hope that you are I hope you can do the assignment, and if let's say you have any question to ask me, or how, and you can ask for my opinion whether your works are good enough or not, or maybe it is understandable or not. So you can also refer to me before you posted the thing. Yeah, it's okay, it depends on you if you want to refer me to not, but if not, you can just post instantly so that I can get more likes. But make sure that by next week, by Tuesday, I want you to upload your poster as well as the proof of the likes and the comments on Putra Blast. Okay, so I think that's all for today, and I will keep you updated for the next session. All right, thank you. Have a nice day.